Okay, so then first speaker is Pierre Louis from RIKEN-AIP. So he will be talking about randomized subspace Newton method. Okay, please.
Thank you very much. So yes, first, thank you for the organizer of this workshop. I'm very happy to be able to present here. And yes, today I want to speak about the joint work with Teruani Fuji and Akiko Takeda from University of Tokyo. And the idea is to, we want to use the Newton method, but on a random subspace. So the idea is, yes, we want to, can we use, instead of having this Newton method on the full space, we want to reduce the size of the problem by considering random subspace at each step and see what we can do with that. So first, I want to introduce the problem, then speak about, quickly I will speak about global convergence. Then I want to speak a little bit more on local convergence and present some numerical experiment and conclude. So the problem is we are interested in minimizing a non-constrained non-convex function. We assume it's twice differentiable. And the gist is that instead of at each step of the algorithm, instead of considering this function f on the full space Rn, we restrict the function to a subspace of dimension s. And you can see that here on the function here in red. So the variable u belongs to Rs. And so how do we choose a subspace? So we choose a subspace using a matrix P. So P is a matrix with a n by s by n matrix. So the rank of P is S. And we took P random. And you can see that, of course, if you just minimize one time, of course, the minimum of the function over U is greater than the minimum of the true function, because it's restricted to a subspace. But the idea is because we iterate, so, and the subspace generated by P is random, we hope that we can converge to the true minimum.
What is X?
X is any point. So it's a fixed point. Yes. So X will be the current iterate, xk, and then when you look for the new point, so xk is fixed and you look for the new point. So yes, the two questions we ask is, can we speed up the computational time? And what about global and local convergence property of the method? So yeah, when the function f is convex, it has already been done. So it was a paper in 2019. And you can see that the iterate is xk plus 1 equal xk minus something. And if you look at the term pk Hessian of S time pk transpose, so this is the Hessian of the function restricted to the subspace. And this Hessian, of course, it's a S by S matrix, so it's easier to inverse. The Hessian of F is an n by n matrix, but here it's only a S by S matrix. So if S is small, then it's much easier to inverse. And yeah, in this paper, what they prove is sublinear convergence for global convergence and local linear convergence if F is strongly convex. So this was what was proved in the paper. And yeah, there was also other paper considering even non-convex case, but in all these papers, to the best of our knowledge, there is only local linear convergence and sublinear convergence, more or less the same as the paper above. So here, because the function is non-convex, what we do is that, of course, the Hessian P time Hessian of F time P transpose, it's not definitely positive anymore, because the Hessian of F could have negative eigenvalue. So we add some regularizer, so eta k, is. Eta k is the parameter so that the matrix is definitely positive. And tk is a step size, it satisfies the Armijo rule. I will detail it later. And so this is based on a paper by Ueda and Yamashita in 2010. So in the original paper, so in the original paper, so there is no random subspace, it's just a deterministic method. And what the author proved was a global sublinear convergence and a local quadratic convergence. So assuming some local error bound condition. And so this local error bound condition, it says that the distance between your point and the local optima is bounded by the gradient, by some term times the norm of the gradient. So of course, if the function is strongly convex, this holds, but yeah, in general, you cannot prove so local local superlinear convergence if you don't have some assumption, extra assumption. So the one they use is this local error bound condition. So the question we ask is, can we extend this result to the random subspace setting? So okay. Sorry. So one thing is clear is that so first at the beginning there was two questions. Can we speed up the computational time? And so this is easy because as you saw, we only have to inverse small matrix, so S by S matrix, and also here when we compute the regularizer, so eta k, we only have to compute the smallest angle value of a S by S matrix. So the computation time is easy to see that will be speed up.
But still, you need a Hessian.
Yes, yeah, I need the Hessian, exactly.
This square.
Yes, yeah. And so we assume we can compute the Hessian easily. So what we see is that more difficult part is for the local convergence. And what we will have is some negative result in this case. So just I want to present quickly two tools that we use. The first one is called the Johnson-Lindenstrauss lemma. It says that if you take a random Gaussian matrix, so all the entries are taken independently with a mean 0 and variance 1 over S, then the probability that the norm is more or less preserved is very high. So it's an exponential that decreases with S. And so in the lemma, this was used a lot in machine learning because it says that if you have a bunch of points in a space of high dimension, you can project this point in a set of a space of dimensions that is proportional to the logarithm of the number of points. So it does not depend on the original dimension, and the distance is preserved. And why is it important? Okay, sorry, we skip. It's useful because what we want to do is that since the matrix P is random, you see that you could have that even though the gradient of F is non-zero, the gradient belongs to the kernel of P. But because of this lemma, we know that with very high probability, the descent direction is zero if and only if the gradient is zero. So this is why it's useful. And one other result we will need is this concentration inequality for random matrix. So it says that if P is random Gaussian matrix, S by N, so of course P times P transpose will have full rank with probability 1. But also if you scale this P times P transpose by some factor 1 over N, it will be very close to the identity. This will be useful. Yeah, so this was I want to explain that. So this is the algorithm. So first we have some initial point, x0. We have some parameter to set. Then at each step, we sample some random Gaussian matrix. We compute the regularized sketch Hessian. So the first term, pk Hessian times pk transpose is the sketched Hessian. And then we get the regularizer. And for that, we need to compute the minimum eigenvalue of the sketch Hessian. But again, if S is small, this is not time consuming. Then what we have is we have some direction, so the Newton direction, and we compute the step size using Armijo rule. So basically, the step size is computed such that this holds, this negative holds, where alpha and beta are parameter. And what is easy to see is because we have this lemma here, this Johnson-Lindenstrauss lemma, what is easy to see is that with high probability, we can compute the next point will be strictly decreasing. We satisfy this inequality. So global convergence is not, I will be fast on this. So the assumptions are quite usual. So the level set as the first point is compact. And the other one is that we assume that at least locally the Hessian is Lipschitz. And so this is the main assumption. And so this is the global convergence result. So it says that at some point, so we have T minimum, so it is the minimum step size. We can prove that with high probability, so the step size computed by the Armijo rule will be larger than this. We have some parameter P that depend on the ratio N over S. also that depend on the norm of the gradient and the norm of the Hessian. And then it says that so yeah, the global complexity is the same than in the paper here. And the trick is that this result holds with high probability. So 1 minus 2m. So m is the number of iteration, exponential of some constant minus s. And sorry, this should be a plus. Sorry, it should be a plus inside the parentheses. So exponential of minus c0 over 4s plus exponential of minus s. And so, yeah, I have to convince you that this probability actually is high. It's close to 1. But actually, it's easy to see because if you assume that the norm between the initial point and the solution grows as some function of n, a polynomial of n, then you can see that you can take the dimension s to be some constant times the logarithm of the original dimension. And you see that this probability will be close to tends to 1 when n is large enough. So actually, for s, we only need to take some logarithm of n. So yeah. So I want to recall you that s is the size of the regularized Hessian. So we take something proportional to the logarithm of n. So actually, if m is really large, then this will be still easy to inverse. And so yeah, this result is, I mean, the proof is not so different. So I will not, I will be fast on this. For me, what is more interesting is the local convergence result. And so for that, we assume that the sequence xk converges to a strict local minima, x bar. What we will show is that the sequence f of xk converges locally linearly to fx bar. And unfortunately, so we cannot hope for superlinear convergence because when the function f is strongly convex, then we saw that we will prove that superlinear convergence does not hold using some random subspace method. And so for that, we have two assumptions. So the first one is Hessian is Lipschitz. And the other one, I mean, that we assume that the size of the subspace S is negligible with compared to n. I mean, you could relax this assumption by saying that S is smaller than some constant time n. This will still work. But yeah, here I just assume that S is negligible with respect to n. And so the other one is a rank assumption. So of course, if the Hessian of f at x bar is has full rank, then linear convergence holds. So this is this is well known. It's very easy, and with random subspace it doesn't change. But here we assume that the rank is at least some constant time n, some constant sigma, and so this is a local, something similar to the local Rebound condition. It says that the value between fxk and fx bar is greater than some constant times the norm of xk minus x bar times some parameter, and this parameter rho can be at most 3. Should be smaller than 3. And actually, this condition is weaker than the usual one because in the usual condition, you assume that either f is strongly convex or that f has some similar kind of assumption, but with rho at equal to 2. So here we are low to we have a more lowest bound here. And what is interesting is that even though the Hessian of f is not semi-defini positive, so if the sketch Hessian will be semi-defini positive. So it says that there is some neighborhood, so B star of the point x bar, and on this neighborhood, the sketch Hessian will be defini positive. And the minimum eigenvalue so depend on the constant sigma, and also some so the minimum positive eigenvalue of the Hessian at x bar, and this holds with high probability. And I don't want to explain the proof, but just the idea is to use the fact that we have the concentration on the singular value of the matrix P, because we know that P times P transpose is close to the identity. And because of that, we know that the weight of the positive eigenvalue will be greater than the weight of the negative eigenvalue on the sketch Hessian. because on some neighborhood of x bar, we know that the positive eigenvalue will dominate the negative one. So this is a very sketchy idea of why this is true. And so once we have this, we can prove some things, some PL inequality. So PL inequality, so if the function is strongly convex, then what it says that the norm of the gradient of the function is greater than this term, so some constant on this term, some f of x minus the minimum of f. So this is similar. It says that the norm of the gradient of the function restricted to the subspace. So this is exactly p times the gradient, and this is greater than some constant times f of x minus the minimum value of the function restricted to the subspace. Well, so yeah, this is something it's a straightforward corollary from proposition 1. And also, what we need also is to say that so the distance of fxk at iterate k, fxk minus the minimum of the function of the current subspace is not too far away from the true optimum. So fxk minus the minimum value of f of xk plus pk transpose u. So here u is a variable. It's bounded below by some constant time of f of xk minus the value of the local minimum. And then once you have this and this, the PL inequality, actually you just copy the proof, usual proof for local convergence, and you get this result saying that the convergence is locally linear, where kappa is some constant between 0 and 1. So this result holds with high probability, but we have also some deterministic version. So if you take the expectancy of f of xk plus 1 minus fx bar, it's smaller than some other constant kappa prime that is also smaller than 1 times the expectancy of fxk minus fx bar. And check the time. And so now what we can ask, what about superlinear convergence? And for this, what we assume is that so the dimension s, so the small dimension s, is satisfy this condition. So it means that s is at least smaller than n multiplied by some constant. And if we have this, what we can prove is that if you take k large enough, then the norm at a point xk, so xk plus 1 minus fx x bar, the norm, is greater than some constant c times the norm of xk minus x bar. And I just want to say a few words about the proof. The idea is to copy the proof for the superlinear convergence in the Newton method. So when you do that, you will have some quadratic term. So you can forget about this quadratic term. And then you will have some term, something like the gradient plus the Hessian times xk plus 1 minus xk. And this term in the Newton method, it's 0 exactly. But here, because we use some random subspace, so this term is the projection on some subspace. And so assuming that, I'll go back, sorry. Assuming that this is true and this is true, then you can prove that you can prove the result. So the projection on the random subspace will have some norm that is not quadratic. And because f is, we assume that f is strongly convex, so this is equivalent. So the theorem is equivalent to the fact that if for k large enough, so f of xk plus 1 minus fx bar is greater than some constant times fxk minus fx bar. So it says that this result is actually optimal here. So yeah, so that's quite unfortunate because it seems that using random space we cannot achieve the same convergence rates for the usual Newton method. But however, so if you look at some experiments, so we did some experiment for super vector regression with a loss function L that is non-convex. And I'll just show you quickly. So this is the loss function we used in this setting. And yeah, the dimension is 1,500, so it's not so big. So I think, yeah, I will do again the experiment with a much higher dimension because I think it will be still better. And so yeah, if you look at the function value with respect to iteration, so in blue you have the usual gradient descent. RNM is just the usual Newton method on the full space, and then we use our method for so S equal 100, 200, and 400, and we get this. So if you look at the iteration, it seems that the method on the full space is better, but if you look at time, so the function value with respect to time, we see that it's faster with our method. And it's easy to guess because, yeah, at one iterate of the full Newton method take a lot of time because you need to inverse the Hessian.
Gradient descent is quite fast.
Yes, yes. Gradient descent is quite fast. And yes, so the paper is on archive, and now what I look for a way to force this superlinear convergence. So at each iteration, I want to tweak the random matrices, maybe using some the current gradient or Hessian information to somehow, I wonder if there is some way to force superlinear convergence with this method. So that's what I am interested in now. And yeah, some reference. And thank you very much for your attention.
Yes. So it's quite surprising to see that S is just log n.
Yes, yeah.
So I just want to know the reason for that. So the Hessian, the eigenspectrum of Hessian decreases quite fast.
Yes, sir.
So can you somehow always say that the eigenspectrum really decays exponentially fast?
So sorry. So you mean for maybe this?
Starts within a few dimensional subspace, right?
Yes, sir. Oh.
Why does it happen? Because Hessian is almost degenerated.
Yes, almost degenerated. Yeah.
But is it always true? Doesn't it depend on the true function?
No, it doesn't depend. No, and I think it's because so you see, actually, so sorry, where is it? I think the size of dimension is not so surprising. So where is it? Yeah, the first slide. So for example, if you reduce p is just one dimension, so p is the direction that is sectioned by the gradient, then this algorithm is exactly gradient descent.
I see.
And so what is so I think for just global sublinear convergence, the Hessian information is not so much important.
In the case of gradient descent, so one-dimensional direction starts from the entire space.
Yes.
But if you restrict the subspace into a S-dimensional subspace, then I don't know, it's not really the same.
Yes. For me, I think the best explanation is that when you look only for a linear convergence on the sublinear convergence, the Hessian is not so much important. What is important is the fact that the gradient does not belong to the kernel of the subspace Pk. And this is true with very high probability.
As long as you can find some decent direction.
Yes, exactly. Yeah. I see. And I think the log n, it comes with respect to this probability here, because the probability decrease exponentially with respect to S. So this is, I think, the explanation.
Then one more question is, so can you make a stochastic version of this kind of algorithm? Now, if it's some.
Yes, I think so, yeah.
In that case, still random projection works in some way?
I think because it will be independent if the random projection is taken independently from the function, then it should hold at least in expectation. Okay. Intuitively, I think it should hold, yeah.
So then, yes.
Just one question. So the random matrix was that Gaussian?
Yes.
What if you change the distribution?
So if it's you could change the distribution. For example, you can make it sparse. Yeah. So each entry is taken as a Gaussian, but then you flip a coin with some probability p. So either it's a 0 or some non-zero in the equation.
Sure.
Then it will also hold.
Okay.
And for the numerical experiment, I think we take some sparse random matrix.
Do you see a difference among them?
At least as long as it's not too sparse, then there is not so much difference.
Oh, good.
Yeah. And also, if the line of the random matrix is a sub-Gaussian random vector, then it's also the same.
And the theory holds.
Yes, it's very the same. Yes.
That's good. Thank you.
Other question? Yes.
Okay, thanks. So you assume that Hessian is low rank, and
sorry.
So you assume that Hessian is low rank. So
yes.
Then so is there any quantity, something like a condition numbers, like the ratio between the smallest non-zero eigenvalue and the largest eigenvalue?
You mean in the
rate of convergence? You have a linear convergence. So then, is there anything, something like a condition?
So for this result, you mean?
Hmm? Okay.
So for the convergence, global convergence?
Yeah. Yeah, global or local anyway.
Well, I think the condition number does not appear. I think in the.
Okay.
But what appears is the ratio n/s.
Okay, so that is a kind of benefit of a Newton method. So actually, it's just a grand descent also achieve the exponential convergence.
Yes, exactly. So it's true that with this negative result, you say what's the advantage of using this method, because you could use some first order method and achieve the same theoretical guarantee. But when we do the experiment, we see that we beat the usual first order method. And I think one explanation is, since actually when you try to prove the superlinear convergence, so you have this term that is the norm of the gradient plus the Hessian times xk plus 1 minus xk. And on the random subspace is the projection on some subspace. And I think if this projection is small, then it's almost like superlinear convergence. Of course, it's not precise, because you can prove that with high probability it's only linear. But somehow, I think when we do the experiment, we see a clear advantage of using this method. So it's possible that the norm of the projection on the subspace is quite small, and then we have something that is not quite quadratic, but almost. I mean, I think it's something I should investigate more.
Okay.
Yeah. Thank you for the question.
I have from article that this kind of random projection has been applied to many different problems so far. And this time S is log n.
Yes.
This is, I think, very strong. But if you see like other problems, is Newton method something special, or for any other methods you have similar?
I think you can do for every method. The problem is like for first order method, if you can compute the gradient, it's not useful, because the first order equivalent of this method will be like xk plus 1 is xk minus p transpose p times the gradient. So you have this extra step of computing p transpose p. However, if you cannot compute the gradient, then you can use the zero order method to estimate the gradient, but on the random subspace. So now we do some also this. We have some paper in preparation where we use this this method for over neural network, and see that we estimate the gradient on the random subspace using this zero order method.
Yeah. Not about optimization, but machine learning prediction. Maybe random projection has been used to support the kind of thing. Do you know the choice of image might be? Well, not log n.
It depends on the decay of the value.
Oh, can't relate.
It is very difficult.
Oh, no, not yet. Interesting. So, any further questions? We started 5 minutes earlier, so now it's half an hour. So you can stop. Then, okay, thank you very much.
Thank you.